All right, and this is the 2020 AMC 12A problem number 6. In the plane figure shown below, 3 of the unit squares have been shaded. I put an X. What is the least number of additional unit squares, that's important, additional, not total, that must be shaded so that the resulting figure has 2 lines of symmetry? Let's think about the lines of symmetry. Can we have a diagonal? No, because it's not a square. There cannot be a diagonal line of symmetry. So the only possible lines of symmetry have to be a vertical line through the center or a horizontal line going this way also through the center. Okay, so let's start with the vertical line. For the vertical line, this one doesn't matter. It's already symmetric, but this one's going to need a point over here. And this one's going to need a point over here. That's 2 so far. Okay, but now we have to go vertical. This one has to appear here. This one has to appear here. This one down here. And this one up here. But this one must also appear here as well. So we added 1, 2, 3, 4, 5 more for a total of 7. Continuing on with the 2020 10A, problem number 10, which was also the 12A problem 7. 7 cubes whose volumes are 1 through 343, which are all the perfect cubes from 1 to 7, cubic units are stacked vertically to form a tower in which the volumes of the cubes decrease from bottom to top. So I start with the largest volume in the bottom and it increases from there. Except for the bottom cube, the bottom face of each cube lies completely on top of the cube below it. Let's try to get an idea of what this looks like. Just draw a quick sketch of a cube. Okay, and then on this cube is going to be another cube, right? And so it's going to sit like this. Something like that, right? And so you can see that the top cube lies completely on top of the bottom cube. Okay, what is the total surface area of the tower, including the bottom that's down here in square units? Okay, the first thing we have to do is that we have to find the edge length, which we said was 1 to 7, and then you're going to use that to find the surface area of the bottom cube. It'll simply be 49, the area of one face, times 6, which is 294. Okay, but what happens when I attach this block here at the next block up? Basically, this block here is going to also be 6 sides, each with 6 squared, which is 36. However, one of those sides is facing down, so we don't count it in the surface area. And then it covers up an equal space on the 7 by 7 by 7 cube, so you're losing an additional area of 36, and you really only have 4 times 36. The problem basically breaks open from here. You simply have to consider that all of the cubes as you go up are going to have this same problem. So when I put the 5 by 5 by 5 cube on here, it will cover an equal space on it as well as on the cube below it, the 6 cube. So we can just add 4 times 25. We'll just do this. Plus 4 times 36 plus 25 plus 16 plus 9 plus 4 plus 1. 10 and 20 is 30. And this is 61 to give 91 times 4 is 364. Add 294 to get 8, 5, carry the 1, 658, which is answer choice B. Are we sure it's going to end that way at the top? Think about the top block, right? It's a 1 by 1 by 1 cube, and it's going to lose one face of itself, and you're also going to lose one face on the 2 by 2 by 2 cube. So it makes sense. This does check out all the way to the end. We can be sure the answer is B. All right, and now for the 2020 10A, problem number 11, which was also the 12A, problem 8. What is the median of the following list of 4040 numbers. You have 1 to 2020 followed by all the squares from 1 to 2020 squared. So how do we approach this? Think of it like a big sequence. And if we want the median of the first 4040, we're going to want a sub 2020 plus the 2020 first term divided by 2. Okay, because that will be right in the middle of the two middle terms. So how are we going to get that? If we take the first 2020 terms, there's obviously 2020 of them. How many of these perfect squares, though, are actually before 2020? Well, at a quick calculation, 45 squared is 2025. There is a trick to numbers that end in 5 when you square them, by the way. All you do is take the tens digit, multiply it by the number after it in the number line. So 4 times 5 is 20, and then you throw 25 on the end. Real quick example, 35 squared would be 3 times 4 is 12 with 25. Continuing on, 45 squared equals 2025. That's going to be a little too big, but 44 squared, which is 89 less than this. So I can subtract 100 to 1925 and add 11 to get 1936 for 44 squared. So then this number is less than 2020. So when we get to the number 1936, what term number will we be on in our sequence? Well, you're going to have all of the 1936 integers from 1 to 1936, plus you're going to have 44 perfect squares, which match up with several of these numbers. So if I add 44, I'm going to get 1980 as my term number. Okay, so now we're at term number 1980. We need to get to term number 2020, which means we have to add 40. And we're at 1936, so when we add 40, we get 1976. The next number being 1977, and that takes us to answer choice C. Okay, and on to the 2020 12A problem number 9. How many solutions does the equation tan of 2x equals the cosine of x over 2 have on the interval 0 to 2 pi? Initially, when I approached this problem, I started thinking about the double angle formulas for tangent, or I could also do tangent of x plus x, so the sum of two angles, and cosine half angles, and thinking about how those things could work. And I tried it around and tinkered with it, and it just didn't look very nice. I didn't really want to continue that path. And oftentimes when you find yourself bogged down with a lot of calculations, it's kind of a sign that maybe that's not the right path. Now, there may be a solution that way eventually, but I just didn't find it enjoyable, so I decided to abandon that course and went ahead and just tried to graph. So let's start with cosine of x over 2. The formula that I like to use for trig is a trig of bx minus c plus d. Trig represents all 6 trig functions, so it can be sine, cosine, anything. A is the amplitude, B affects the period of the graph, and for right now we don't care about the phase shift or the vertical shift because these don't have them. So in our problem, we basically have cosine of 1/2 x. Now the half is the B value, and the standard period for cosine is 2 pi, and 2 pi over B is equal to the period. If I put a half here, I'm going to get a period of 4 pi. Let's graph that and see how it looks. So we really only care about from 0 to 2 pi. So we are going to go 4 equally spaced marks, 1, 2, 3, 4. And since this is 4 pi, this will be 4 pi, 2 pi, 3 pi, and pi. But we only want this part right here. So we will have, for cosine, you start at your peak value of 1, and you fall to equilibrium at the first value, the first critical value. You fall to your minimum at the second one, and back up to here, and then up to here. But again, we really only need to go this far. Okay, next up, well, we'll just graph it anyway. Next up, we're going to graph tangent of 2x. Now, don't forget, tangent has a vertical asymptote whenever its denominator is 0. So when cosine would be 0, that's when it normally has its vertical asymptote. So when is cosine equal 0? At pi over 2, right? And at negative pi over 2. So if I set 2x equal to pi over 2, x will equal pi over 4. This is my first vertical asymptote. It'll be located right here. Now, there's another one at negative pi over 2, but we don't really care about that. It's going to give us, kind of I guess we care, it's going to give us another vertical asymptote at negative pi over 4. So 2x equals negative pi over 2 divide to get this. And tangent, if you forget, it's got two vertical asymptotes and it looks a little bit like x cubed. And so it just kind of starts down here approaching negative infinity, crosses over in the middle and approaches positive infinity. So it's going to do that right here, cross over right in the middle, and there's your first solution. Now, we can also learn that this is going to repeat every pi over 2, because from negative pi over 4 to positive pi over 4 is a distance of 2 pi over 4. And so I'm just going to travel 2 pi over 4 this way, and there will be one here. Another 2 pi over 4 this way. We're now at 5 pi over 4, and then 7 pi over 4. And then you think you don't need to go past this, but you probably should just to see what happens. You're going to get 9 pi over 4 for your last vertical asymptote. So it's clear that between here and here, it's going to come up and cross here, and it's going to come up right here and cross in the middle. You get one here and one here. You're going to come over here and cross over here. And you will come right here. Yeah, right here. And lastly, it's going to have this one solution right here. Now, you might not notice this one if you didn't graph the last asymptote. That's why it's a good idea to graph it. This does take place on the left-hand side of 2 pi because it actually doesn't cross over until you're actually at 2 pi. It will cross over the 0 mark. And so it's going to come up through here like this. So we get 1, 2, 3, 4, 5 solutions, and the answer is E. Okay, and now for the 2020 AMC 12A problem number 10, the last problem in this set. There is a unique positive integer n such that the log base 2 of the log base 16 of n equals the log base 4 of the log base 4 of n. What is the sum of the digits of n? Now, a lot of times in the past, I would too panic when you see a log problem. But actually, they just rely on the basic rules usually. And if you just throw the basic rules at it, you can usually break the problem down and make it solvable. So let's start with this. I wish these were the same base. Well, then we should use change of base formula. Let's make them both base 2. This one's already in base 2, and this one can be written that way. We can say that it's equal to log base 2 of log base 4 of n over log base 2 of 4. Okay, if you don't remember change of base formula, it's log base a of b equals log base n of b over log base n of a. So the b goes up, the a goes down, and you choose whatever base you want. So in this case, this expression is going up, this 4 is going down, and we chose the base of 2. Now, this becomes log base 2 of 4, which we know is 2. If you forget how to calculate logs, log base 2 of 4 equals something. It's 2 to the something equals 4. So 2 to the something equals 4. It must be 2. And so therefore we can replace this with 2. So now we will have log base 2 of log base 16 of n is equal to 1/2 log base 2 of log base 4 of n. Now the half can be put up top here to become the half power, which is the square root. We now have the same base on these logs, so their inside parts must be equal. And we can say log base 16 of n equals the square root of log base 4 of n. Now, we want, again, the same base so we can work with it. So let's make the 16 into a base 4. We'll now have log base 4 of n with the n going up and the 16 going down to become log base 4 of 16. Again, 4 to the second power equals 16, so this is really 2. Now we have the square root of log base 4 of n equal to this expression. We can now substitute something so we can think about this. Let's put u. It'll be u over 2 equals the square root of u. We'll cross multiply and square both sides. U squared equals 4u. Then subtract 4u and factor out a u to get u times u minus 4 equals 0. U will equal 0 or u will equal 4. So now we will say log base 4 of n, which was u, right, is equal to 0. 4 to the 0 equals n, then n can equal 1. And we can take 4 as well, and log base 4 of n equals 4. 4 to the 4th, which is the same as 16 squared, is 256. So n is equal to 256. Now, we have these two possibilities. We have to check them out. If I put 1 in here, what is log base 16 of 1? It means 16 to some power equals 1. That power is 0. And now we have log base 2 of 0. This is a problem. Zeros are not allowed inside of logarithms. So n equals 1 is not a valid solution. Not to mention, it's not a possibility in the answers. Let's try 256. If we plug 256 in, it's 16 to some power equals 256. Well, the power is squared, we already know. So this will say log base 2 of 2 equals log base 4 of 256, which is the inside part right here. 4 to what power equals 256? Well, we just did that. It's 4 to the 4th power. So this expression equals 4, and that means the 4 is going to be right here. Log base 2 of 2 is 1 because it's 2 to some power equals 2, which is the first power, and so is this for the same reason. Therefore, 256 works, but we want the sum of the digits of n. 2 plus 5 is 7 plus 6 is 13.